And just to this, or to spoil the thing from the beginning, we know very little about it. And this gives a potpourri of things we have been doing, and just to show that we know too little to actually do some quantitative suggestions at this stage, and I will give you a flavor of what our way forward will be. Having said that, that doesn't mean we have nothing to tell. There's quite a few interesting things just as a background. So those who are used to permeability being a static rock property, you measure it and then you can use it to make assessments of what you can produce or stick it into a modeling software. Forget it. If you deal with super hot stuff, it's becoming a dynamic property interacting with different things there, like temperature, stresses, and so on and so on. Then, as we have very little data from active system, the way forward for us has been learning from fossil ore-forming magmatic-hydrothermal systems, porphyry, copper, and the like. They have been studied a lot. There's a plethora of data of what has happened in these things millions of years ago, and we developed numerical models to understand how they formed and could test the results that we obtained against field observations. So these models are quite good, but they are not good enough for what we're talking about here, mainly because we have not fractures included. You see here a piece of core from IDDP2, almost at the bottom of this thing, and there's fractures, there's open fractures in which fluids were circulating. And this is usually not included in numerical modeling as explicitly represented things. So if we want to understand what is happening there and how these would respond to operation, we have to include it in modeling. And this will be the last part of my talk to give you a flavor of what's going on there. So let's see if this proceeds here. Yes. So going back 2 days, in my first talk, I mentioned the key role of permeability in shaping geothermal systems. So the upper one was the key slide on high enthalpy resources. And it basically tells you permeability controls enthalpy that you can get in such a system. And this is because at the heat source, you have conductive heat transfer, which is a pretty limited supplier. And then how fast you can circulate fluid past the heat source determines how much heat it picks up, and that determines how hot it gets, how much enthalpy you can produce. So when it comes to supercritical resources, and that was from the work of Sam Scott some years back, permeability controls the extent, the enthalpy, and the flow rate in such resources. And this is quite nice, but this was all again done in the porous media limit. So there is no feed zones, no nothing in here. This is just giving you a first order impression of what these things or how geologic factors such as permeability control these things. So as I said, these conclusions are for the porous medium limit, but what is the role of fractures and faults? When you go to Reykjanes, when you have IDDP2, or when you go to Hangit, where there will be IDDP3, they target faults as their feed zones. And these things have to close down when they get too hot or when the loading is too high. And at the moment, we have very little understanding of what is going on there. And on top of that, John Burnell on the first day made some assessments of how much fluid you can get into a well when you drill into super hot conditions. And he found that the limited permeability may actually lead to not so exciting flow rates. So his conclusion, or one of the remarks, was hotter is not necessarily better. And all of us are enthusiasts for the hot stuff, so we want to know if we can't do better than this. All right, then the first thing I highlighted on the first day was that there is a temperature dependence of permeability. So if rocks are heated very highly, then there will be a brittle to ductile, or more precisely, a brittle to plastic transition. And when the rock becomes plastic, it can deform such that it closes pore connectivity and fractures, etc., so that reduces permeability. This has been cast into quantitative numbers by Dan Heiber and Steve Ingebrigtsen by guesstimating what it should look like. And so here is an example from their landmark paper, quarter of a century back. So this is temperature, this is log permeability, and if you have a porous medium subject to heating and some normal crustal strain rates, you're supposed to see something like this, up to about 360 degrees, 400 degrees C for quartz-rich rocks. You have a more or less constant permeability, and then this brittle to plastic transformation kicks in, and the permeability decreases until it's very, very low, basically impermeable. Now, we have been using that, and where this starts is a function of the rock type. If you have basalt, this onset temperature is shifted to much higher temperatures, can be 550 degrees or so. Or if you have a high strain rate, you may actually break the rock repeatedly. In particular, if you're in an extensional regime, this will also shift this thing to higher temperatures. So fluids can access higher rocks under those conditions if you have, for example, basalt or an actively extending regime. Now then, with time, people did more studies, and this became, well, not obsolete, but it was realized it's too simple a view. And then Marie Violet and her people in Lausanne are quite active. And so they found, for example, that if you deform basalt or granite, you may actually, when you go into the plastic regime, you may nevertheless have some dilatancy for temperatures as high as 600 or 700 degrees C. So porosity increases, although you're actively deforming the rock in the plastic regime. So there's some potential that we don't lose that permeability that rapidly. Or then Watanabe et al. In 2017 also highlighted that if you have fractures in there, they not necessarily close rapidly if the confining stresses are not too high. Or more recently, as far as I understood it, they also found that, of course, if you have fluid, you may actually have dissolution of asperities, etc., on the fractures, and then it decayed. The permeability nevertheless deteriorates. But this basically tells you there's a wide open field of research for understanding permeability under supercritical conditions, be it porous or be it fractured media. Oh, then a prime example where you have fractured media and porous media under nominally supercritical conditions are the so-called porphyry copper ore deposits. On the left is a cartoon of what we currently think how they are forming. So the idea is you're sitting above the subduction zone typically. You have hydrous magma intruding and having a big intrusion at, say, 5 to 10 kilometers depth. This contains dissolved in the silicic melt up to 5% or so water. And if it starts to crystallize, most of the minerals that are crystallizing are anhydrous. So the water has to go somewhere, and it will exsolve as bubbles, and these bubbles will collect at the top of the intrusion. And that's when you have more than them. After a while, actually, you have so much of that the fluid pressure here is so high, you will break the overlying rock, and you will inject a mixture of melt, crystals, and these aqueous fluids under the magmatic temperatures, essentially. Crystals and melt will get stuck because they're more viscous. This makes these typical subvolcanic stocks here, which porphyritic textured rocks, because you injected crystals and melt. The crystals are the porphyritic crystals in the porphyry, and the melt crystallizes fine-grained ground mass. But the aqueous fluids will actually crack the overlying rock, make more hydrofracturing, and escape. And going from high temperature to much lower in the surroundings, they will precipitate minerals. So these fractures, as you can see here, this is an example of a typical porphyry copper ore sample from Batu Hijau in Indonesia. And you see various types of mineralized veins. The earliest ones, for example, or let me take the laser pointer here, like this one, they actually are heavily deformed, sinusoidal, or they show very irregular networks. They are later cross-cut by more straight ones. And even this one here cross-cuts this one, although it looks just vice versa. But when you have a close-up here, you will actually see what's ongoing. The yellow stuff here is not the vein. It's actually the alteration halo, and the actual vein is just a thin line in the middle that goes through the earlier white one here. Now, these are called A veins, A for the earliest ones. And the idea is they form when the rock is nominally ductile, but fluid pressure can actually break even a ductile rock. So these are forming at near magmatic temperatures, 600 or even 700 degrees. And then when the system later cools, you have more brittle type fracturing and you get these straight veins. Now there's a plethora of data we can obtain, fluid inclusions, isotopes, you name it, alteration, reactions, etc. And these have been studied in great detail so we can learn about the formation conditions. These data were in place about 10 years back when we had our numerical code development evolved so far enough that we could actually start simulating that. But we had a lot of detours and we found that you cannot simply do a porous medium simulation, put some magmatic fluids into a simulation domain and then see what happens. Rather, we found that mechanical effects that influence permeability are really essential, and there are mainly three of them. It's the temperature dependence that we talked already about. There's a depth dependence put forward by Steve Ingebrigtsen and Craig Manning. And you have to have some failure criteria as a function of fluid pressure here on the vertical axis and differential stress on the horizontal axis to get an idea of how the rock here will break and allow fluids to percolate through them as a function of fluid pressure, stress evolution, and temperature. Now let me quickly introduce these three elements. Well, and just for geothermal, so about the depth dependence. So the blue curve here is the sort of average for a normal crust. So on the horizontal axis is log permeability, on the vertical is depth from 0 to 20 kilometers down. Then we know that at the permeability of 0.1 millidarcy or 10 to the minus 16 meters square is approximately the boundary between conduction-dominated and convection-dominated heat transfer in the crust. So here is the field of conduction dominance, and in normal crust, this is reached already at a few kilometers depth. Now, I said this curve, and let me go back, is for normal crust. And there's a second curve here, and this is for so-called stimulated crust. There we had earthquakes, or people tried to make an EGS system, or you had a dam and then filling it with water and the water infiltrating the rocks underneath, and then you can measure permeability. And you see there is a difference of about 2 orders or so magnitude difference. Stimulated crust is more permeable than normal one. So in the stimulated crust, you have convection-dominated stuff, and so this is the interesting one for geothermal and also for the porphyry fluids to get out here. All right, so permeability with depth, I just explained the two different things here. And I think not much more to say, just you see there's huge scatter of the data. So this 2 orders of magnitude is just a very crude estimate. Similar, the permeability for the normal crust, but that's the best we have at the moment, and we put it into our model. And the temperature dependence, this comes from mostly Bob Fournier, reflecting on brittle to plastic or brittle to ductile transition in the Earth's crust. And these would be here some differential stress curves at different rock properties as a function of temperature or depth, assuming some geotherms, and that at some stage you get to the brittle to plastic transition, and then you cannot sustain any more differential stresses. So these curves go this way then. So whether you look at the normal crust, you will see this as a function of depth, and then it will be somewhere at 10 kilometers or 15 kilometers. Or you go to near a magma where heating is extreme, this remains mechanically more or less the same, and it should have more or less this effect on permeability. And finally, in order to get from this curve to that curve, you have to have some criteria when the crust will fail or a particular fold will fail and get more permeable. And then you can employ a nice concept introduced by Rick Simpson and Steve Cox. So on this diagram, you have differential stress on the horizontal axis. And on the vertical is the so-called pore fluid factor lambda, which is basically hydrostatic fluid pressure divided by lithostatic pressure at the point that you're interested in. So if you have hydrostatic pressure and you assume a density of water of 1 gram per cubic centimeter and of rock of 2.5, then 1 divided over 2.5 is 0.4. So hydrostatic pressure is approximately here. Or if you're in a ductile regime where you do not have connected porosity that comes to the top, you have fluids under lithostatic pressure, then you're here at 1. Fluid pressure divided by lithostatic stress is basically. Then there are 3 curves here for normal faulting, strike slip faulting, reverse faulting, and these indicate where for a given differential stress or how high the fluid pressure has to be to make this thing fail, slip, and then perhaps get some permeability increase because the 2 walls of the fracture are rough. When it slips, they don't match anymore, and you get free space in between. So take-home message here is, in the brittle regime, you have to go a little bit over hydrostatic pressure to make any of these fail. If you go to ductile regime, you have to have fluid pressure higher than lithostatic. Now, when you put this into the model and let it run, so down here is the magmatic intrusion. It crystallizes, releases fluids. They collect at the highest point. And when there is enough fluid collected, it pushes against the pore walls and builds up pressure. And at some stage, one of these failure criteria kicks in and releases fluids. Then on the way up, they will try actually to push the rock apart, and they will make this magmatic hot fluid plume above this hydrous magma. So this is definitely not Icelandic basalt. This is something like in the Andes or something like that, where you have a lot of water in the melt. And they travel upwards, essentially cracking the rock. These fluids are hot. With time, they will also heat the zone where they are ascending. And so with time, actually, you get a nominally ductile rock thing here. And you need the fluid pressure at above lithostatic to crackle it and let the fluids rise here. Now at the top here, depth dependence of permeability kicks in. The upper part is pretty permeable. You have groundwater, etc. And the heat from this magmatic fluid plume initiates convection up here. And that cools the top of the plume and makes this mushroom shape here, which resembles the ore shells you typically see. Now, the duration for these blobs moving up in such a model, where you map essentially fracture processes to porous media, is about 10 or so years, in the order of years or tens of years for one blob moving up here. And there's a lot of things that this model predicts in terms of temperature distribution in the ore deposit, which would sit here, evolution of the fluid from magmatic to later meteoric, and so on, which you can test by field observations, by fluid inclusions, by oxygen isotopes, etc. And several of the things that this model predicted, that we published 10 years back, were actually successfully tested on field examples. And so we think this is pretty nice, and we caught a lot of the essence of the process. Well, all nice, but as I said, this is porous medium, mapping fracturing to porous media. And this has a lot of implications that are probably not very correct. For example, these blobs rising in a few years or tens of years is probably pretty incorrect. If you make a real fracture here, it will rise up within minutes hours or days, and then the hot fluid is up here. So we get the time scales wrong, and a few other things like the succession of veins, etc., can simply not predict it. So that's one of the reasons why we want to move forward to more fracture-oriented permeability representations. And we had quite a few studies on that, including the PhD by James Patterson, who will join GNS later this year. So you get someone who knows how to do this stuff. This is essentially a little video that should turn around, but it doesn't. So this is now at low enthalpy conditions, nothing supercritical or so. And what James did is he put a fracture into the crust. And if it doesn't connect to the surface, you should expect more or less elliptical size. So this, I think, is a few kilometers this way and 1 or 2 kilometers that way. Has a certain permeability inside. There's a geothermal gradient in the porous medium surrounding it. And then we looked at what happens in the fracture zone here. And it starts to convect. If you have low permeability / transmissivity, you get convection cells that have a large diameter. But you get, in the upflow zones, positive thermal anomalies at the top, and in the downflows, negative thermal anomalies at the bottom. Looking from the top, you then see that the hot stuff is conducted into the rock matrix, making these thermal anomalies along the fractures, as is the cold stuff. So you have hot and cold zones along a fracture. And you can imagine EGS, you want to hit a thing like this. It can be 6 or 10 degrees hotter than average conditions at this depth. And this makes quite a difference already for EGS. So then maybe I just get rid of this and then, see, so this was the video. It shows now turning around how the thermal anomalies look, etc., etc. So we then went to a setup of several fractures. Now you see here 5 of these elliptic fractures sitting somewhere in the crust. They are in an echelon style arrangement, and they sit in an essentially impermeable matrix. So there is no hydraulic connection between them. Again, there's a geothermal gradient in here, and then James looked what is happening. Now we have a look from the top down, so we will see the fractures just as lines. They're extending perpendicular to what we see here. So in the video, we now look what the thermal evolution is in there. So in the beginning, not much is happening, then convection starts, and we see how the upflow zones make hot things around the fracture and the downflow zones cool things. And now in the different fractures you have this, but they will start to see each other because heat conducts into the surroundings, and then it lines up across the hydraulically not connected fractures, but there is now a concerted sort of convection going across them without having any hydrologic connection between them. So that was quite an interesting effect, and that contributes actually to the enhanced power output that you see in strata above that are not penetrated by these fractures. Similar thing you can even get, so these were fractures that have a homogeneous permeability or aperture, etc. And if you now use one that has a heterogeneous aperture, which is probably much more realistic, so we have a log normal distribution of aperture or across or on the fault plane, this gives you an idea on the heterogeneity, 5 of them. Nevertheless, in spite of this flow channeling, you expect here the thermal structures or convection cells across these 5 fractures will align or will line up and overcome the obstacles given. So that was quite an interesting learning, but this was, as I said, at low enthalpy conditions, more relevant to Central Europe. So getting such fractures into one of our high temperature models would be quite desirable. James pushed that even further. and looked at single fractures, and we are now looking onto the fracture plane. It's connected to the surface, so cold rainwater can come in here. The fracture as a function of depth responds to loading, so that it follows, it has a tapering aperture downward, following the Barton-Bendis relationship. And then, as I said, rainwater can trickle in here. It starts to convect, and where you have, and thermal stresses are also considered. So where cold water is flowing down, the wall rock will actually thermally contract, and aperture will widen, making channels where you have increased downflow. At these points, then the stuff gets down and hits the lower bottom, where at the beginning of the simulation, at about this depth here, everything was closed. Now we will have thermal stresses. It cracks its way down and makes a convection cell that can mine new heat. This process has been speculated for some of the low enthalpy resources in Iceland. Gundny, I think, was one of the people putting this forward. And we were very pleased seeing that, at least for the model assumptions we had here, we can reproduce this kind of postulated process. So for fractures, we have now quite a few things in there. We have all the temperature pressure dependence of the fluid properties. We have mechanical tectonic thermal stresses that can be included, heat transfer. We can have some sort of simplified cracking model here, etc. So that's becoming quite interesting for going hotter. And the most recent stuff is from Eduardo Pizzuli's PhD thesis, defended just about, well, slightly more than 10 days ago, no, about 10 days ago. So what Eddie implemented is actually hydraulic fracturing. Not the simple version we had that we just saw in James's thing, but Eddie really includes now a fracture that has water in there. And this water, the properties of this water respond to temperature and pressure. Now, fractures, hydraulic fractures, if they sit in rock, they have a finite vertical extent. Sorry that this thing pops up all the time. It's difficult to explain. And then inside the fracture, you have essentially a more or less hydrostatic pressure gradient. And outside, you have this more or less lithostatic pressure gradient. So that means inside here, at about the middle of the fracture, these two things will be in pressure equilibrium or mechanical equilibrium. But on the top of the fracture, it's overpressured with respect to the rock, and at the bottom, it's underpressured. Buoyancy on top of that makes this fracture to have this tadpole shape. And just to mention it, this is massively over-exaggerated here. The width of this is just in the order of millimeters, whereas the height of this is 500 meters. So then, due to this, the fracture will actually impose stresses at the top and can crack the rock open. And at the same time, it will close at the bottom, and this makes this fracture rise if some force balance here tells you that the thing is buoyant. And you can actually model it, and Eduardo did that very nicely. And this was actually the first time ever that this was done with the full water properties in there. And depending on what your thermal gradient is here, these things will arrest or rise rapidly over very large distances. So they can rise within minutes or hours for 2 kilometers or something like that, if the thermal state of the crust allows them to do so. So Eddie did some diagrams that show how far they can rise, etc. And I cannot summarize it. It's pretty complicated stuff, but we're working on getting this published so that you will see it at some stage this year. Then what is also interesting from this work, after having understood all this with these buoyant fractures, so they were rising in the beginning, and here is now an intrusion at some depth that is cooling and heating the rock surrounding it. And the interesting finding is there's actually also areas where you have reversed buoyancy. So fractures want to go down, and that's highlighted here in the color coding. So there may be areas near our intrusions where we are looking for super hot resources here in their vicinity, where actually natural fluids, or where fluids that you inject into fractures may want to go down instead of up, and this may perhaps be an interesting way of stimulating things without bringing too much pressure into the system. Right, to wrap up, where are we standing? So, well, permeability at superhot conditions, and I hope I could show this, is a dynamic property with emergent behaviors. So it's nothing like you assign 1 millidarcy and then you do your modeling. It responds to interplays between temperatures, mechanical, tectonic, and thermal stresses, heat transport, mineral dissolution, precipitation, failure, and so on and so on. So this is by no means trivial. And fractures are key, but we haven't understood their role and behavior at all. We're just, as you saw, trying to get into this a bit better. So we have now, thanks to people like Eddie and James, many tools in place to study this, but the parameter space, as well as the problem space, is huge. So we have to extend these tools to work at superhot conditions, or some of them to work at superhot conditions, and then we can study things like, well, fracture interactions. Those of you who saw Benoit's talk on in the first session will have seen at IDDP2, you have these 3 inflow zones, and depending on what the thermal and pressure state in the well is, they will start influencing what you produce, where you produce from, what you produce significantly, and this will actually change if in that model we make these fracture subvertical structures and things like that. So there's a lot to be understood here. In particular, as John Burnell said, there is pretty much counterintuitive behavior if we include these realistic representations. We have to consider fracture versus porous medium flow. It will be very different for understanding how we can extract heat from that, convection patterns, the response of fracture hosted feed zones to production, the interaction of different feed zones, and so on and so on. So there's plenty of things to do, but we'll try our best to get this done or approach this in the near future. So thanks for your attention. I hope I got you an interesting view on what is ongoing in this field.